What's up, guys? Welcome back to my channel. Welcome back to GCSE Paradox. I hope you all saw my last video, which was a math paper, random math paper, and just like last time, we are doing a random physics paper right now. We are doing MJ 2011 97242. So, guys, let's begin. Yeah, it's an A2 level paper, guys. So, say what is meant by a field of force. So, field of force is just an area or region where any particle or body where particle experiences a force. That question was kind of nothing. So let's move on to the next question. Gravitational fields and electric fields are two examples of field of forces. See one similarity and one difference between these two fields of force. Well, so you all know the formula for gravitational and electric fields, right? Uh, Fg, which is gravitational force, is gmm upon r square, and electric force is kqq over r square. Well, as for similarity, can you see this, guys? Both the forces are inversely proportional to the square of the radius. So, and the similar thing applies for fields. So you can say that the field strength is inversely proportional to radius square, which is r square. As for difference, guys, y'all know gravitational fields are just for masses, and masses only tend to attract each other. But electrical fields can be used from both positive negative charge combination, or positive positive charge combination, or negative negative combination. Both of these are repulsive, but positive negative is attractive. So difference, the only difference possible is that you know gravitational force is always attractive. Always. Sorry for the spelling, I'm just kind of rushing with the paper. But electric fields, on the other hand, can be both attractive or repulsive. Right, guys? I hope you understand this much. Two protons are isolated in space. Their centers are separated by a distance r, and each proton may be considered to be a point mass with point charge. So we just have to determine the magnitude of the ratio, the force between protons to electric field and gravitational field. We just determine determine the formula, which was kqq upon r square for Fe, and gmm upon r square for Fg. So we can just simply divide both of these. Kq, there are two protons, so it's gonna be q square. I hope you understand, guys, why. Because there are two protons with the same charge, so q into q is q square upon r square divided by g, same goes for the masses, divided by r square, which is equal to kq over r square, kq square over r square multiplied by r square over gm square, and r square end up getting cancelled. So we have kq square upon gm square. K is 9 into 10 raised to 9, and q, which is charge on proton, is 1.6 into 10 raised to minus 19 coulombs. G is the gravitational constant, which is 6.67 into 10 raised to minus 11, and mass of a proton. Mass of a proton is, now let's see guys, just like me, I'm not sure with the mass of the proton, so we'll just confirm it with the data sheet. Yeah, 1.67 into 10 raised to minus 27. So the mass of the proton is 1.67 into 10 raised to minus 27. Now if we just substitute this in kq square upon gm square, let's see what we get. Alright guys, so I'm doing the calculation and I get 1.2 into 10 raised to 36. So this is the final answer guys. Let's move on to the next question. Say what is meant by a mole. Oh, we know the usual, the basic chemistry definition of a mole. Mole is just, it's just amount of a substance. But since it's for 2 marks, there has to be 2 points. So you know that point where we refer to the carbon atom. So you have to use that point. That 1 mole contains same number of carbon atoms as in 12 grams of carbon 12 isotope. So yeah, these are definitions. Y'all will have to memorize it. Two containers A and B joined by a tube of negligible volume as illustrated in this. So okay, so we are given the volumes and the temperatures. So what do we have to find? Calculate the total amount of gas in mole of in the containers. So we can just use PV equals nRT for both of these, and we can let's say we get N1 and N2, so we can just simply add N1 and N2 in the end. So let's calculate. For container A, N equals, okay, just for reference, N equals PV upon RT, which is equal to 2.3 into 10 raised to 5, the pressure is given in the question, into 3.1 into 10 raised to 3. Now over it's in centimeter cube, so multiplied by 10 raised to, let's say, from meter, decimeter, centimeter, so centimeter to meter is 10 raised to minus 2, so it's gonna be into 10 raised to minus 6 for centimeter cube. Alright, divided by R is gas constant, which is 8.31, multiplied by temperature, which is 17 degrees Celsius, guys. Remember the SI unit of temperature is kelvins, so we need to add 273. And for, let this be N1. For container B, we do the same thing, and we'll use these values, but the value of pressure would be the same, 2.3 into 10 raised to 5. And I guess we get N2 as 0.420, and N1, We get N1 as around, yeah, I'm just calculating. We get it at around 0.296. So we just add both of these. We get 0.716. Let's move on to the next question. Oh, capacitors. Capacitor consists of two metal plates separated by an insulator as shown. Okay. These are the metal plates. This is insulator. This is the insulator. The potential difference between the plates is V. Okay, the variation with V of the magnitude of charge Q on plate is shown. Okay, make sure you look at these units. It's microcoulombs, millicoulombs. Explain why the capacitor stores energy but not charge. So, guys, you know, uh, capacitors. Capacitors rely on the fact that charges separate. Correct. So, for capacitor to be able to store a power or energy, it needs to separate the charges so that one of one of the plates is positively charged and one of these is negatively charged. So to to separate these charges, energy is required. But if you if you look at the overall charge of the capacitor, you'll find out that the resultant charge is zero, because the charge on this plate, the magnitude of the charge on the upper plate is equal to the lower plate. This means the the only difference is the sign. So let's say it's plus x on this and minus x coulombs. The total is actually zero, so capacitor cannot actually store charge. The thing it does is it creates an electric field, but to set up this electric field, charge separation is required, and to separate those charges, energy is required. So this energy is what the capacitor stores. Alright, guys, so um, I'll tell you the answer from the MS. So the MS states that there's no resultant charge because the charges on the plates are equal and opposite, so the charges effectively cancel out. But there is charge separation and energy is stored. Use figure 3.2, which is the graph, to determine the capacitance of the capacitor. So we know that Q equals CV, so capacitance is dq by dV, or the gradient. So let's take 2 points and calculate the gradient. I'm taking this point and this point. If you calculate the gradient, So if you calculate the gradient, it comes to be around one. It comes to be around 1800 microfarad, and what we need to consider this milli over here. So it's just gonna be 1800 into 10 raised to minus 3. Sorry, not 1800, it's gonna be 18 into 10 raised to minus 3 minus 0 divided by 10 minus 0 x minus y2 minus y1 upon x2 minus x1. So you get 0.018, and this 0.018 is with these units in farads, but I guess they want it in microfarads, so you will have to multiply 18 to 10 raised to minus 3 by 10 raised to 6, from farad to microfarad, so you'll get 1800 microfarad. The loss in energy stored in the capacitor when the potential difference V is reduced from 10 volts to 7.5 volt. So from 10 volts to 7.5, somewhere around here. Yeah. So what we know is, we know the capacitance value, which is 1800 microfarad, and if you remember, there's a formula for the energy stored, which is half CV square, and we can just use this formula. So energy at 10 volts minus energy at 7.5 volt, this is gonna be equal to 1/2 into 18 into 10 raised to minus 3 farads capacitance multiplied by 10 square minus half into 18 into 10 raised to minus 3 farads into 7.5 square, or in short, I'm just using half C V1 square minus V2 square. So if you calculate, you'll get you will get 0.3 0.39. So 0.39. Okay guys, I've done a mistake. It was actually 1.8. It was 1.8 into 10 raised to minus 3, so 1.8. 1.8. So what we get is Yeah, so we actually get 0.039 joules, but as you can see they want it in millijoules, so we just multiplied by 1000 or 10 raised to 3, which gives you 39 millijoules. Alright guys, so this is what happens when you don't concentrate on the units. So 3 capacitors, each of capacitance 10 microfarads. Just writing it down. Initially the capacitors are uncharged. Potential difference of 12 volt is applied between the points A and B. Determine the magnitude of the charge on one plate of capacitor X. Alright guys, it's for 3 marks. So the first thing you should do is calculate the overall capacitance. So let's just calculate the overall capacitance for this parallel combination. So this is gonna be 10 plus 10, which is 20. So this entire circuit is equivalent to alright, because we calculated this, which was the overall capacitance of the parallel combination. Now we have just the series part. So overall capacitance or the C effective is gonna be 1 upon 10 plus 1 upon 20 and the reciprocal of this. So if you calculate, you'll get 20 by 3 microfarad. And we know Q equals CV, which is equal to 20 upon 3 microfarad multiplied by 12 volts, which is 80, which is 80 microcoulombs. And this 80 microcoulombs charge is uh, let this be Q just for the diagram. So this 80 microcoulomb charge is what this capacitor X receives over here, plus Q minus Q, and plus Q charge, the total of the plus Q charge in both of these, and minus Q would be the total in both of the negative plates. So that is why plus Q is what the positive charge, positive plate of X gets. So we just want to calculate the magnitude of charge on one plate. So that's just gonna be 80 microcoulombs. I hope you get it, guys. Just to revise, it's just that each capacitor in series takes the entire charge, which is Q. So 80. That's why we use the total potential difference in the circuit. Moving on. First law of thermodynamics. So it's positive delta U positive Q and positive W. So it's increase in internal energy. Plus Q is increase, or rather supply of heat, because this heat is external, and W plus W is the work done by the system. But since it's W, the work will be done on the system, so that uh, there's increase in potential internal energy. So it's work done on the system. Now, state what is meant by specific latent heat. It's for 3 marks. So, specific means per unit mass, and latent heat is just change of state without change in temperature. So, the change, latent heat is the energy required to change state of unit mass of an object without change in temperature. So guys, 3 marks, 3 points. Use the first law of thermodynamics to explain why the specific latent heat of vaporization is greater than the specific latent heat of fusion. So vaporization is similar to evaporation, and fusion is similar to melting. So guys, in evaporation, a liquid turns to gas. So there is far more separation between the molecules in uh, gaseous form compared to liquid, and that separation is even less in solids. So solids to liquids means molecules, this is for fusion, molecules are separated but only by a small distance. This distance is less um, compared to the separation in vaporization. So in short, I'm just trying to say that there is more separation of molecules that happens in vaporization compared to fusion. That's why more energy is required. Since there's more energy required during evaporation because there's greater change in separation, which means there's even greater change in volume from liquids to gas. There is greater value of delta V, and we all know work done is P delta V. If delta V is greater, means even W is greater. That's why, since liquid to gas, which is vaporization, has greater delta V, there is greater, the specific latent heat is greater than specific latent heat of fusion for vaporization. A bar magnet is suspended vertically from the free end of a helical spring as shown in figure 5.1. Okay, one pole of the bar magnet is situated in a coil. Coil is connected in series with a high resistance voltmeter. Magnet is displaced vertically. So this is a variation of the induced voltage. State Faraday's laws of electromagnetic induction. So it's just that EMF is proportional to the rate of change of magnetic flux, summarized by this one derivative equation. So EMF induced is proportional to rate of change of magnetic flux, which is basically the magnetic field lines cutting through the coil. You find us not to explain why there's a reading, so we just need to explain why there's even a reading. So I guess the only reason is just that the magnetic field due to this magnet, let's say they are like this. Don't you think when the magnet goes up and down, the velocity changes because the extension keeps changing? You know, we have SHM where we have an equation for velocity which is trigonometric, something like v sine omega t. So velocity is not constant. Since velocity is not constant, the rate at which the magnetic field lines cut these coils, even that's not constant. So since there's changing velocity, there's changing rate of magnetic field lines, there's EMF induced. So the answer is gonna be moving magnet has field lines which cut through the coil and induce EMF. Next one is what I just answered, why the reading varies. So the reading varies just because the speed of the magnet varies. So there is change in rate of the magnetic flux or the magnetic field lines being cut. And while the reading has both positive and negative values, as you can see, the reading goes from positive, 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 and then after this point it becomes negative, then again positive, positive, positive. So the reason is that just because uh, you know the magnet initially when the magnet moves downwards it's going into the coil, and afterwards when this is the final position of the magnet, this is the final position after it comes down, it will again go back up, correct? Because the spring will pull, the spring will try to pull the magnet up again. That's why it's going into the coil, then coming out, then going into again. So both of these have an opposite effect. So the reason is magnet keeps changing direction of motion with respect to the center of the coil, thus changing current. This part is not required, this is just for your understanding. So yeah, to determine the frequency of the oscillations, use the graph. So yeah, we can just calculate the time period, and we know that time period is 1 upon frequency. So time period is 0.75 seconds. I hope you guys know how to calculate time period at least. It's time it takes for one complete wave. So starts from here and ends over here. That's why these two start and end points. So the time is 0.75 seconds till that point. So frequency is going to be 1 upon time period, which is 1 upon 0.75. So it's 1.33 hertz. The magnet is now about to rest, and the voltmeter is replaced by a variable frequency alternating supply. So just for easy understanding, it's just that this voltmeter is now replaced with an alternating supply, and this magnet is now come to rest. So it's at rest somewhere in the coil. So let's see, don't you think if there's a magnetic field induced in the if there's a magnetic field generated in the coil because of this alternating voltage, there'll be a magnetic field inside the coil. This magnetic field will somehow affect the magnet, because this magnetic field of the coil will interact with the magnetic field of the magnet. Thus, due to this interaction, there's always a force, the motor effect. So, what we have to answer is completely different. It's just that the frequency of the supply is gradually increased. So, guys, we can just use the resonance concept that we had in the oscillations chapter. This magnet will already be oscillating up and down due to the force because of the interaction of the magnetic fields, the motor effect. And if there's an applied frequency on top of it, which means there's force frequency, there are force vibrations, they can either be in excess or some vibrations are wasted. And I hope you all remember this graph. Like at the natural frequency, the oscillations have the maximum amplitude. It's something like this, correct? So it's the same graph here. Just we are just applying it in the concept of electromagnetic, the motor effect. So this is the natural frequency, and we'll just draw a graph like this with the maximum value over at this point. I hope you understand, guys. It's just simple thing. So, and yeah, these the oscillation amplitude never becomes zero, correct? So we can just draw both of these at any random points. Moving on to the next part of the question. Name the phenomena illustrated. So I just said it's resonance. Say one situation where the phenomenon named is useful. So it's useful in producing ultrasound from that crystal, correct? You have that. So ultrasound production from quartz crystal. Guys, there are many more uses and applications of this resonance. So make sure you check your textbook. And alternating supplies connected. Okay. Variation with time to current, correct. The frequency. So first we know this is equivalent to this format. I equals I naught sine omega t, correct? Both of these. And we know, so by looking at this, we know that omega is equal to 380. We can use this simple fact to calculate frequency. We know that omega is 2 pi by t, which is 2 pi f. So 380 equals 2 pi f, and f is going to be equal to 380 upon 2 pi, which is equal to 60 hertz. So yeah, the answer is 60. Now the RMS current, root mean square. So you'll have this formula in your textbook. IRMS is I naught upon root 2, where I naught is the maximum value of current. So we know I naught is 9.9 because we have learned these graphs where this is I naught and this is minus I naught, where I naught is the maximum current according to this equation. So we'll use 9.9 as I naught. I naught is 9.9 amperes. So 9.9 upon root 2, which is equal to 7 amperes. To prevent overheating, the mean power dissipated. Mean power is just average power, which is half P max. The maximum half of the maximum power in R must not exceed 400 volts. So half of P max should be equal to 400 watt maximum. Calculate the minimum resistance of R. So we have RMS value of current, which is 7. We also have the original value of current, the maximum value, which is 9.9. So we can use either of these. Depending on the usage, we'll change the formula. Let's say we are using I naught. So I so P equals I square R. P max is equal to I naught square R, which is 9.9 square into R. this is gonna be P max, and we know the mean power must not exceed 400, so P max should not be equal to 800 watt. This is the maximum, so this is equal to 800. So R is equal to 800 upon 9.9 square, which is 8.2 ohms. Now guys, just to let you know, there's a different method given in the MS. uh, just like we have IRMS as 7, we have this concept of RMS. There's even a concept of mean power, that mean power is equal to IRMS square R. So instead of just, so it's the same formula over here. We just used IRMS instead of I naught, and we'll have the mean power if we use RMS. So 400, we'll use the mean power 400 as given in the question, equals 7 square into R, and R is equal to 8.2 ohm. Again, same answer. Now comes the quantum physics chapter. Say what is meant by de Broglie wavelength. So de Broglie wavelength is just wavelength of any particle, of any moving particle. I'm not sure why it is of 2 marks, but maybe because it has to be a particle which is moving. An electron is accelerated in a vacuum from rest to a potential difference of this, so that the final moment of the electron is this. So let's see, we have voltage, we know voltage, we have the charge of electron, which is 1.6 into 10 raised to minus 19, negative 1.6 into 10 raised to minus 19, and we have voltage, we have charge. We know voltage is work done per unit charge, so work done per unit charge is Q delta V. Oh yeah, so energy is 1.6 into 10 raised to minus 19 multiplied by 850, because I'm using this E equals QV. So we get energy as 1.36 into 10 raised to minus 16. And we need to find the final momentum. For that we need the final velocity. We can just use this energy conversion. E equals half mv square, which is equal to 1.36 into 10 raised to minus 16 is equal to half the mass of the electron, which is 9.1 into 10 raised to minus 31 into v square. If we calculate, we'll get v as we'll get v as 1.8 into 10 raised to 7. This is the final velocity. Now we just need to calculate the momentum, which is mv, which is 9.1 into 10 raised to minus 31, the mass of electron, multiplied the final velocity, which gives us 1.57 into 10 raised to minus 23, which is equal to 1.6 into 10 raised to minus 23 Newton second. So guys, it's proved now, hence proved. There might be some other methods for this, but as of now I guess this is the easiest method. So calculate the de Broglie wavelength. So we know that rho is E upon C, which is hc by c lambda, because energy is hc by lambda from energy equals hf. This formula is there in your textbook. So rho equals h upon lambda. Lambda is Planck's constant upon p. We can just use the previous values and the value of Planck's constant from the data booklet to get this. And we get the answer as 4.1 into 10 raised to minus 11 meters. This is a de Broglie wavelength. So the final answer is 4.1 into 10 raised to minus 11. Moving on, this time I'm excited to demonstrate the wave nature. So guys, remember for the particle nature we use a photoelectric emission, but for the wave nature, diffraction is probably the best. So we have this gap or slit, and you have a screen. The screen is maybe made of carbon, a carbon film, and we have this electron beam which shoots electrons, and this carbon needs to have a screen which is fluorescent so that we can see the tracks of the electrons. And what else is required? Yeah, I guess we can just conclude that when an electron hits, uh, there are chances that it might behave like waves, and it might land in two different positions, and there might even be concentric rings on the circle formed because of the electrons acting like waves. So yeah, this is pretty much it. Now, nuclear physics. Say what is meant by the binding energy of the nucleus. So binding energy is nothing but energy required to separate nucleons. Till infinity. So that the energy equivalence of 1 U is 930 megajoules. So 1 U is 1.66 into 10 raised to minus 27. We know Einstein's formula, E equals delta m c square, which is 1.66 into 10 raised to minus 27 into 3 into 10 raised to 8 square, which is the speed of light. So if we calculate, we get 1.49 into 10 raised to minus 10. And they want it in mega electron volts. So if you divide this by 1.6 to 10 raised to minus 19 and multiply this by 10 raised to minus 6, you will get your answer in mega electron volt, which is 933 mega electron volt, which is similar to 930 mega electron volt. Now, using this data, they want us to calculate the binding energy of deuterium. Deuterium is made up of one proton, one neutron, and the mass of the nucleus, the mass of the particle of deuterium is this. So we can just find the change in mass. So 2.0141, the final mass of deuterium nucleus, minus the mass of its nucleons, individual nucleons. So there's one proton, so 1.0073, this, plus the mass of one neutron, 1.0087. which is minus 1.9 into 10 raised to minus 3 U. So this is the change in mass, which means the mass of deuterium atom is less than the mass of individual nucleons making it up. And this, uh, from the previous question, we know that 1 U is 930 mega electron volt. So 1.9 into 10 raised to minus 3 mu is equal to 1.9 into 10 raised to minus 3 into 930, which is 1.8. Now they want to calculate the binding energy per nucleon of zirconium. So for zirconium, we can repeat the same thing, but first we need to find the number of protons. So number of protons in zirconium are 40. Neutrons are 97 minus 40. Using this, which is 37. Sorry, 57. And the mass of zirconium is 97.098. So if you calculate the change in mass of zirconium, you will get, let's do it on the next page. Mass of zirconium minus the total mass of the protons minus the mass of the neutrons. So if you calculate, delta M comes out to be 0.69. I'm not thinking about any signs over here. And if you convert this into binding energy, you will get 0.69 to 930, which is 640. But they want per nucleon, so we'll just divide this by the number of nucleons, which is 97, and in the end we'll get 6.61 mega electron volts. I hope you understood this, guys. So first we just found the delta M using the number of protons and neutrons, and we find the total mass of that, and we subtracted from the total mass of zirconium atom. Then we convert it into energy by multiplying it by 930. Then we find the energy per nucleon, which is total energy divided by the number of nucleons. So we get 6.61. So I guess, guys, we are not doing section B. So that's it for today. I hope you like my videos, and I hope you like my channel. Channel's name is GCSE Paradox. Signing off.